an important aspect of this wave particle duality is the uncertainty principle. This has many repercussions for physics, but the simplest one involves the position of a particle and its speed. Heisenberg's uncertainty principle states that one cannot know the position and speed of a particle independently of one another. Here we go. So not only did people, quantum physicists and classical physicists, have to digest the fact that quantum mechanics was probabilistic, but here was a quantification or a quantization of the uncertainty and the uncertain nature of quantum mechanics in this uncertainty principle formulation or formalization. Okay, so there is a even a quantification of what this uncertainty is in the form of the uncertainty principle. So this basically says that the better you know the position, the worse you will know the speed of a particle, and vice versa. So if you know the position, you cannot know the speed. Certainly you'll have some limit, some uncertainty limit on the speed. And if you know the speed, you cannot know the position with certainty. You will have some uncertainty on the position. And together, it's postulated in the uncertainty principle. So if you know its speed precisely, then the particle could be located anywhere. This principle is quantitative. I mean, is it really anywhere with equal probability? No. Again, there's a probability associated with finding that particle at a certain position. So it's not like you knew the position was here, last you checked, and it's going to be somewhere totally different, like on the other side of the universe or anything. Not quite like that. But there's going to be a probability associated with where you expect to find this particle, okay? So this principle is quantitative, does not apply only to position and momentum, but also to energy and time and other pairs of quantities that are known as conjugate variables. There is this concept of conjugate variables in physics. It is a particularly important consequence of the energy-time uncertainty principle that empty space can give birth to short-lived particles that spring in and out of existence on a time scale controlled by the uncertainty principle. So by the by, this whole situation of the uncertainty principle, this whole situation that we talked about, in fact, yesterday we were talking about how nothing can actually have quite a few things in it, especially because of the pair of particles and particle-antiparticle pairs being allowed to kind of go in and out of existence. Actually, nothing can be kind of busy with things happening. We just don't know maybe all the time that that's happening, and until we take sort of a measurement, right? So basically this situation of the uncertainty principle has a lot of very important consequences. It can actually come to the rescue in some situations where otherwise you would have had a tough time explaining how that can happen, right? So this is the reason why. So if you ever need nothing to have something, then look to the uncertainty principle. This is the reason why particle physicists expect the vacuum to possess energy. So vacuum is technically maybe not always totally nothing. Vacuum could maybe have things going in and out of existence, right? So maybe there is something going on there, full of mystery. In other words, there should be a cosmological constant. So cosmological constant, we talked about it,